Hello everybody, and welcome to the next lecture of 6837. Today we're going to continue our discussion of computer animation by talking about particle systems and ordinary differential equations. Essentially, in this part of our course, we're going to be talking about how to incorporate physical, or at least physically plausible motion into animated content, largely for the kind of secondary things that you see in the scenes, special effects, and those sorts of things. So, as a bit of a review from our previous lecture, recall that there are a lot of different ways that we can animate a scene in computer graphics. So for instance, kind of building on the machinery that we developed for spline curves, we might define a keyframing procedure where an artist or an end user describes an animation by giving the pose of the characters in the scene at a few isolated points in time, and then the computer system fills in the motion in between. In procedural rendering, we write a piece of code that generates motion. Remember our basic example being a clock face with the ticking seconds and hours hands. Today, we're going to talk about the third method, which is physically based animation. This is one of the most challenging techniques for animation mathematically, but also artistically. Essentially, the animated world doesn't have to be completely physical by the standards of the physics department. And oftentimes we actually want it to be artist directable. And so physically based animation is this kind of polite term that's intended to indicate that the animation is based on the laws of physics, but sometimes extends on them in different ways. That is to say that the motion that you see in animated film might not be something that you could actually replicate in the environment around you. So we're going to talk about physically based animation quite a bit in this course, and it's a pretty popular topic for people's final projects. Today, we're going to talk about particle systems. These are some of the really basic techniques for physically based animation, but actually do form the basis for how things like smoke, water, fire, sparks, and so on appear in animated content, especially in video games and software that needs to produce animations quickly. We'll see that particle systems are often built in a pretty heuristic fashion. That is to say that even though we're going to talk about Newton's laws and F equals ma and how to capture that digitally, the actual forces involved in the physical systems that we often set up in an animated scene really aren't based on experimentation. They're just based on getting the look that we want. So in some sense, this is quite liberating, right? We can define the physics of our world any way that we want to get some cool, interesting, or visually compelling content. In our next lecture, we're going to build upon this particle system idea by talking about how you can simulate a piece of cloth and build up models called mass spring models that capture a lot of the really complex motion that we see in the physical world using just a few simple rules. This is only going to be scratching the surface of the physically based animation world. Physically based animation is a really deep and challenging discipline, and you could easily fill multiple computer graphics or even engineering courses with all the techniques that you need to simulate smoke, water, hair, things crashing into each other, rigid bodies, and so on. So some of the advanced topics include things like continuum mechanics, fluids, plastic material, and so on, finite elements, and other topics. In this course, we won't be covering that type of motion in any deep fashion, although I encourage you guys to do some extra reading, and I'm always happy to point you toward interesting resources. This tends to be a popular topic for course final projects, by the way. But methods like finite elements are covered in other computer graphics courses at MIT and in other departments as well. So for instance, my graduate course 6838 will cover some of the basic mathematics of FEM, which is called the finite element method. And that's sort of the basis of many of the physical simulation tools that are out there. Another really key tool for physical simulation and physically based animation is rigid body simulation, like simulating billiards and things bouncing off of each other and so on. This class won't get too close to that kind of motion, although it's particularly important for video games and that style of content. Okay. So in the physically based animation world, our basic goal here is to simulate physics by solving the equations of motion. And the basic equation of motion, of course, is going to be built on Newton's laws, right? F equals ma. And these are going to give us motion of rigid bodies, fluids, plastic deformation, and so on. Sort of by definition, physically based animation is physically plausible, right? It's realistic because you're really trying to simulate the physical dynamics in a scene. On the other hand, like we talked about in the previous lecture, physically based animation is difficult to control. So for a simple example, let's say that I'm simulating a bouncing ball. So here we see the path of a ball bouncing through space. And let's say that I want to animate where my character is standing on this side. They throw the ball, and I want it to bounce off of the ground and land in a trash can. Okay, so that might be really critical for the plot of my movie for whatever reason. I want, this physical interaction to happen. But if I use physically based animation tools, then I have to solve what's called an inverse problem, right? And what that means is if I know at like time t, my ball should end up in the trash can, I have to figure out the initial conditions of my physical simulation that would actually achieve that motion. And that can be quite challenging in practice. So even though physically based animation is popular, it's also hard to control, and this can make for a lot of frustrations when it comes to collaborating with artists and other people that are more concerned with the look than the technical content in your film. When we talk about physically based animation, there are many types of dynamics that are involved. Today, we're going to focus mostly on really simple dynamics of just points moving around. So I think in your intro physics class, probably you learned about this sort of a model when you talk about planets, right? And models of gravitation. Essentially, you think of a planet like a tiny point with a lot of mass. But there are other types of dynamics out there, and many of these are worth exploring and worth incorporating into computer graphics systems. So a simple example might be rigid body dynamics. So in rigid body dynamics, you're simulating not just points of mass, but actually the geometry. So you have to account for things like inertia, which can be really important for getting realistic motion, right? If I throw a cube or spin a cube on its side or whatever, obviously the orientation of that object matters a lot. But if I want to account for the geometry of the rigid object that I'm moving around, this will obviously be more expensive computationally. And if I want to raise the bar even higher, then maybe as I throw that box against the wall, it actually dents a tiny bit and deforms, in which case it's no longer a rigid body, but rather deformable. So in this case, we would be simulating things like clothing, fluids, smoke, and so on. And as you can imagine, this is some of the most challenging physics to simulate in practice. And that's because I can't just keep track of like the position of the bunny here. I need to keep track of every vertex of this 3D shape separately as the bunny melts, because they all could move on their own paths. Incidentally, this bunny is called the Stanford bunny. And the Stanford bunny is one of the sort of typical test cases that we use a lot in the computer graphics world to test things like physically based animation. So if you Google around, you'll see some fun examples of the bunny lighting on fire, melting, maybe a whole bucket of bunnies getting shaken around and colliding and so on. It's just a fun 3D test model. If you're curious, I believe the actual physical Stanford bunny, it is a physical object that was 3D scanned a long time ago by Mark Lavoie at Stanford. It's like a terracotta bunny, and I think it's actually at the Computer Museum in San Jose, California, but I could be wrong. Okay, so today we're going to focus on just that first category, which is point dynamics. And so here we're going to think of all the physical bodies that are moving around in our universe as just little infinitesimal points of mass. We often call these things particle systems for obvious reasons. They look like particles moving around. And our goal is to get somewhat physical motion. Again, remember that phrase, physically plausible motion. We're not after the world's most accurate physics simulator. If you want to do that kind of thing, there are plenty of courses here at MIT that can help you learn about those sorts of problems. But instead, we're just trying to learn how to get cool looking physical motion without a whole lot of computation. And One of the remarkably beautiful things about particle systems is just how easy it is to do that sort of thing. So, for example, if you look at the animation on the slide today, if you look, this is, I think, a pretty physically plausible, maybe fountain kind of animation, right? You see lots of particles moving around. They're going on arc-shaped paths. There's some kind of complex geometry going here. But really, behind the scenes, each of the particles moving around in this fountain here is actually moving independently. I believe in this case, literally each particle is just following some preset path, and the particles don't interact with one another. And that's the really interesting thing about these particle systems, is that with just a little bit of physics, you can get some really complex motion, which is quite compelling from an animation perspective. Okay, so let's start by defining some vocabulary words, and then we'll dive into the details here. So a particle system is basically just a long list of little points that are flying around in space during our animated content. And so the particle system is typically composed of a few pieces that interact with one another. So first of all, there's a unit called an emitter. An emitter is a thing in my scene that's generating these little particles that are going to start moving around. So for instance, if I'm simulating a sprinkler like the previous slide, maybe I have an emitter that generates a new little particle of water once every 1/10 of a second. I have a force field, so maybe like gravity is sitting outside of my physical system and acts on each of the particles in the system independently. Or maybe there are forces that act on the particles together, like springs that couple their motion. And now we're going to integrate the law of motion. Typically, this is F equals ma, right? Newton's laws, to actually get the position as a function of time. The word integrate here, I think you're used to seeing, the word integral from calculus class, and indeed, it basically comes from the same root. The idea is that F equals ma gives you some description of the derivatives of your physical system, right? A is the second derivative of your motion. And your goal is to integrate that out and get left with not the acceleration of your particles, but rather the position as a function of time. And then finally, one additional piece of particle systems that tends to be quite useful is to add some randomness. So maybe the particles don't just move in some deterministic fashion, but actually a random number generator kind of perturbs their motion a little bit. Even if it's just totally random, the physical world around us is also quite random, and this can make for some very plausible motion. Again, for the 8th time, our goal today is not physical accuracy, it's physical plausibility, and those are not quite the same thing. So here's a great example. So here's another, we're big on sprinklers today. I think that's the simplest possible particle system. But here you see an animation of a sprinkler, and notice that I think this is a pretty plausible sprinkler. I think if I saw this in my yard, I wouldn't blink. But really, all of the particles are actually moving independently with each other. They just have randomly drawn initial velocities that are sending them in different directions. And from there, they're just following parabolic arcs. So just by nature of having many particles moving around, even if they're moving independently from one another, we actually get some pretty nice looking motion in this scene. Similarly, here is a simulation. Simulation's even maybe a little strong here. A visualization of fire using particle effects. Here, I think the motions of the particles are, prescribed to have this nice swirly behavior. And moreover, the way that this scene is rendered is just using some clever tricks. So for instance, maybe the artist prescribes that toward the bottom of the scene, I should render my particles using a yellow color, and then in the middle, red, and in the upper part, gray. Now, is this how physics works? Well, I don't know. If you're a creationist, then maybe. But from a high level, of course, the way physics works is that there's some simple laws that are determining the motion of particles as a function of time. and those get integrated forward. And the fact that like smoke looks yellow, red, and gray, depending on where you are in the fire here, is a byproduct of the physical system. But in our setup, the artist is just prescribing it, saying like maybe, when particles reach y equals 1, then suddenly their color changes or something like that. This obviously is not physically accurate, but the amazing thing is that we're able to do a pretty good job of getting something that looks okay without a whole lot of work in this setup. Okay. Now, one thing that's worth noting about particle systems is that they don't have to be physics at all. So another great example of particle systems involves simulating humans or agents moving around as particles, right? So maybe I come up with a long list of rules that sort of determine the motion of animated characters as they move around in a scene. Maybe people don't want to walk too close to each other. So there's some repulsive force that happens if you come within a certain radius. Maybe you tend to turn your head if you are close to another human at a certain distance and they're visible. Maybe there's certain rules about, one of my favorite papers in the computer graphics world, I'm going to digress for just a minute, involves modeling this really simple scenario where I have a thin hallway and there's two humans. Here I'm looking kind of down at them from above. My humans are a little chubby. And they have to walk past each other. Now, the humans that I've drawn are circular, but in reality, I think humans are closer to ellipsoidal. And of course, there's a problem, which is that if these two people just walk forward, their shoulders are going to bump into each other. And so instead, what happens if you walk past somebody in a very narrow hallway is that you have to rotate a little bit and then inch past each other and then keep going. And so maybe in your particle system, you model the position and orientation of a human actor, and you actually have rules that try to figure out that just by avoiding collision, you have to rotate in order to pass. There's some really fun, almost psychological studies, or I don't know the right term here, that actually study that dynamical system and try to figure out in our brains what sort of rules we're applying, maybe coupled with social norms and other very latent things that are built into us from a young age. But more generally, particle systems are used to simulate, flocks of birds, humans moving around in a shopping mall, all that kind of stuff. And in that case, it really is this funny version of artistic modeling. The artist can specify the different forces that affect the particles, in this case, like the people moving around in the scene, and then just set them loose. We're going to start with the simple stuff today, and then in our next class, we're going to show how if you have a piece of software for a particle system, you can use it to set up a simulation of a piece of cloth. So the way that we're going to do that is we'll think of our cloth, if you zoom in close enough, like a triangle mesh, just the way that we've done in our previous assignments in 837. And essentially, our proxy for our cloth not wanting to deform too much is to take each of the edges of our triangle mesh and think of them like little springs that are attaching to one another. And so by simulating these vertices coupled by springs moving together in time, you actually get really plausible, nice looking cloth simulation like what you see on this slide. And cloth simulation is one of the big challenge problems in physically based animation. It's one that a lot of computational effort and research has gone into. And the results are just amazing, right? So here's a video clip from Ron Fedke's group at Stanford showing a cloth simulator at this point from actually quite a few years back. And you can see that we're able to capture the dynamics of the system quite well. Cloth is a really interesting challenge because there's so many different dynamical things going on. So first of all, the piece of cloth itself has some dynamics. It doesn't want to stretch or compress too much. Sometimes you call that style of dynamics developability. But another challenge in the cloth system is that you have to be able to handle collisions. So one of the really difficult parts of simulating a physical system happens when two physical objects bump into each other, because you have to detect that that happened and resolve the special forces and impulses that happen to repel in response to that kind of motion. And one of the big challenges with cloth is that the cloth can intersect itself a bunch of times all over the place. And so detecting and resolving self-collision in cloth is a really challenging problem to do right. And it's one that I think is just this giant headache when it comes to writing code. Going down our grab bag of different physical simulation kind of problems you might encounter in computer graphics, another popular one is fluid simulation, like simulating smoke and water. And indeed, even water can actually be plausibly simulated using certain particle system techniques. So the name for these types of systems is smooth particle hydrodynamics, or SPH, if you're in the know. And SPH software or algorithms are intended to simulate water or fluids by simulating the motion of little particles. Now, obviously, those particles are not molecules of water. That would be a little ambitious. There's a lot of molecules in a cup of water. But somehow, I think the fuzzy word that we use is packets, right? So you can kind of see it here. So we have this little pipe that's outputting water into a cup, and these little coarse spheres are representing the tiny particles of water that are moving around in the simulation. One physical term that might be useful, you hear it a lot in computer graphics talks, is the distinction between Lagrangian and Eulerian fluids. In this class, when we talk about particle systems are Lagrangian. So just as a tiny digression, if you want to describe a bucket of water using the laws of physical motion, there's actually two different ways that you could do that, right? So one way would be to think of yourself as simulating, riding along inside of the water, following these little packets of fluid around, right? So in Lagrangian physics, you have these little particles that are interacting with one another, and what you're tracking as a function of time is where they go. And in Lagrangian physics, the actual software code you end up writing looks a lot like the particle systems we'll talk about today. Now, in Eulerian physics, you do a different thing, which is you take your bucket of water, you chop it up into a grid, and now the grid remains fixed. So rather than following particles around as they interact and swirl in this big bucket of water, instead, I'm going to think of myself like a little barnacle and just counting the number of particles that move past. So maybe if I'm representing the velocity field of the water, then I'll do that at like a fixed XYZ location rather than one that's moving along with the particles. This corresponds to something we'll call Eulerian physics. So there's this divide in physical simulation between Lagrangian and Eulerian. And the basic high-level message is that particle systems are Lagrangian. They actually follow stuff moving around. But there are also a lot of Eulerian fluid methods out there too, which would like take all of space, divide it into a grid, and then maybe keep track of something like the density of your fluid as a function of time at a fixed location in space. And fluid simulations are really reaching these incredible heights in terms of visual fidelity and so on. I think we've all seen that in blockbuster Hollywood films. Here's another cool clip, and you can see actually in this case, this video clip is made by coupling together Lagrangian and Eulerian fluids. So the Eulerian fluid is being used in the bulk of the water to keep track of some of the large motion. But if you look at the fluid hitting into the lighthouse here, it emits some spray, and that becomes Lagrangian particles. Particles are used all over the place in video games. So for instance, I think one of the more obvious places where you see them is in boxing games. You hit the character and, fluid comes out of their mouth and so on, a little gratuitously if if you ask me. But you can see the particles in the particle system, for example, in this EA game. So let's watch a tiny bit of their trailer. I'll turn down my volume. And in fact, one of the major aspects of the new physical systems that are used in video games is just how accurate and physically plausible they are. So you can see here the characters are sweating, there's spray coming off of them. I think the other really impressive part of this particular trailer, which is now a couple years old, is not just the dynamic blood, sweat, and tears, but also the rendering in this system, right? I mean, the skin of the characters is reflecting the scene around them and so on. But really all that's going on behind here is particle physics, which is relatively straightforward, actually, relative to some of the other cool features in these video games. We'll also see that you can use particles to simulate stuff like hair. So there, we're going to think of hair, it's relevant to your instructor, but as a long chain of particles linked together with little springs and integrate those forward. So the high level point here, pun intended? I don't know, is that essentially particle systems really arise in a variety of situations. Everything from fairly heuristic methods that maybe somebody has prescribed and hand-tuned a model that seems to create cool-looking motion, to real simulation techniques like SPH that are based in the laws of physics and actually kind of replicate what happens in the physical world. Both sides of this extreme just boil down to integrating ordinary differential equations, which we're going to talk about in today's lecture. Okay. So as we've already talked about, a particle system is just a collection of point-like masses. We can attach whatever information we want to each point, right? It doesn't have to just be the position. It could be velocity, maybe the age of the particle is useful, color, and so on. The motion is influenced by both external force fields like gravity and maybe internal forces like springs. You can make the particles with generators or emitters. These are synonyms, by the way. One detail that is worth noting is that typically your particles in a particle system have a lifetime. Otherwise, you'll continue to emit particles, but they'll never go anywhere, and you'll overload the memory in your computer. And finally, the one last thing that's worth noting is that particles are often independent from one another. We'll see that it's actually not necessary to model really complicated dynamics. It's good enough to just model individual objects moving without any knowledge of one another and still get pretty plausible, nice looking motion. And the final thing is we can render our particles any way that we want. So we'll see at the end of today's lecture that maybe rather than rendering a particle as a point, we draw it like a little billboard flying past, can create even more complex looking scenes. Again, not physically accurate scenes, physically plausible scenes. Okay, so let's set up some pseudocode and see what a particle system might look like for that sprinkler example that we already saw. So the first thing that I could do is build up a linked list of my particles. Remember that a linked list, if you took 6006, is a data structure that holds on to a long list of data that can grow arbitrarily. Some people might keep their particles in an array. That's perfectly valid, but the advantage of keeping your particles in a linked list is that you can keep adding to them as your physical system evolves. And now maybe I have some constants around, like the spread in terms of the randomness and the directions that the particles get, or the spread of the color values and so on. And now I'm going to physically simulate this system by moving forward in time. So we're going to talk about time steps, like little differential changes in time from one frame to the next in my animation. And we'll do a few different things. First, we might generate a set of particles, right? So this would be like the role of the emitter, right? So emit might be a better word than generate here. So maybe it makes a new particle, sets its position to be the origin, right? So there's the origin. Chooses velocity. Here you can see that spread constant getting used to randomly perturb the initial velocity of the particle, sets its color randomly, and adds it to the linked list of particles. Here the ordering of that linked list is not terribly critical. And now that we've done our emitting, we need to actually do our simulation. Well, how do we change the position of a particle? Well, we know that, position, the derivative position is velocity. So if I multiply velocity by a little unit of time, I get an approximation to the change in position. Similarly, the change in position, well, that's acceleration. Remember that by Newton's laws, F equals ma, acceleration, maybe in this system, is just given by acceleration due to gravity, and then we draw. Okay. I've included in the slides a link to a little demo where you can play with a particle system at home. It's kind of fun to click around and see that you can get some nice looking motion, even though your particles don't even talk to each other. There's no intelligence in this particle system whatsoever. So now let's get down to business. Let's talk about the math behind how we can simulate particle systems that are more complex than a sprinkler with a bunch of particles that don't talk to each other. And in order to do that, we're going to talk about ordinary differential equations. So in an ordinary differential equation, the thing that we're trying to find is a function x of t. X here is just a long list of all the unknowns in my problem, and they're evolving as a function of time t. So in an ordinary differential equation, we have some relationship between the derivative of x in time and maybe the values inside of x or time itself. And oftentimes in ODE, by the way, this is abbreviated as ODE, the input and the output are as follows. The input is that we're given the configuration of our system at some time t naught. We can call that x naught. That's like the input to our ODE solving software. And then the output is to find x of t as a function of time for time bigger than t naught. So think about our physical system. Maybe I have a system like a spring, like two particles connected together by a spring. I'm given their position and velocities at time 0. And now my goal in my simulation is to simulate those springs wiggling as a function of time. So this is the world of ordinary differential equations in a very small nutshell. Now, if you already kind of know where I'm going with this, we're going to simulate F equals ma, you should be asking a question, which is, but Justin, the left-hand side of this equation here, it only contains one derivative, right? But F equals ma is a second order equation. There's two derivatives, right? A is acceleration. So if I have a piece of software that can solve the equation on this slide, is that actually all that useful for solving Newton's laws? Now, the answers to this question is obviously yes, given all the setup that I've given you. But it's not totally obvious from the outset here. So remember that F equals ma, where a is nothing more than the second derivative of x with respect to time. And well, we're close to being in the setup from the previous slide, right? X and f are vectors that change in time and space. So we're given f and m, we're trying to find x. And the question is, why is it okay for me to only solve first order differential equations if there's a 2 setting here? Somehow that doesn't make a whole lot of sense. And here's how we can do it. So we're going to use a very typical trick in the world of ordinary differential equations. And that is to introduce additional variables to our problem. So what we're going to do is say that x, remember this is really x of t. I apologize to Isaac for writing on top of him a little bit. I'm going to define a new function v of t. I'm going to define that to be the derivative of x of t with respect to time. And I'm going to say that I'm going to write a physical simulation system that simulates v and x simultaneously rather than just x. So what can we do? Well, we know that v is dx dt, just by definition. But now, what do we know about Newton's law? Well, we know that maybe I take f over m, right? So that's d squared x over dt squared. But we know that dx dt is v, so really this is what? It's dv dt. Hopefully you all followed what I just did there. All I'm just saying is that rather than writing acceleration as the second derivative of position, I can instead think of acceleration as the first derivative of velocity and velocity as the first derivative of x. Okay, and so if I couple all those things together by the magic of PowerPoint, here's what it looks like. We get this system of equations, which says that the derivative of x in time is v, the derivative of v in time is force divided by mass. So all I did was a mathematical sleight of hand. This is a first order system of ordinary differential equations. The word system here refers to the fact that there's more than one unknown, right? There's x, which is a vector, and also v, which is another vector. So in some sense, we can view there as being a trade-off, right? On the one hand, I could have a second order system with maybe 3n unknowns. So here, why is there a factor 3? Well, if there's n particles, I need their x, y, and z positions as functions of time. So that's 3n unknowns. And by applying the trick on this slide, I can replace this with a first order system with 6n unknowns. So in other words, I can make the number of dimensions of my ODE problem larger. That's what I pay, but what I gain is the ability to write it as a first order system. There's only one derivative here, whereas I started with a second order system. Okay. So that's a typical trick that we do in graphics world. So again, we can call this reduction to first order. This is just fancy language for f equals ma. So why do that? Well, what it means is that if we write a piece of code for just solving first order ODEs, which feels easier than second order ODEs, we can actually use it to solve a second order ODE by first writing it in this form and then solving this equation. Now, we have to be a little bit careful about, like, in math, sometimes you talk about the difference between something being necessary and something being sufficient. And this is a great example. So what did we just show? We showed that if we have a piece of code that can solve a first order ordinary differential equation, we can use that piece of code to solve a second order ordinary differential equation after passing it through this particular reduction. What we didn't say is that that's the best possible algorithm, right? So it could be, and indeed it is the case, that there are algorithms out there that are specifically for second order ODE and do really, really well for physical systems. That's an advanced topic, and it's one that's worth exploring if you're excited about computer animation, especially physically based animation. But the point is that they're not necessary. They just can make your simulation higher quality or more efficient. But it's good enough to just do first order. And so in your assignment, you're going to implement a first order integrator, and that'll actually be enough. So as a bit of notation, one thing we can do is we can take all of our positions and velocities and stack them together into a giant vector, big X. And big X is like 2 times the size of little x, right? Because it contains all of the positions and all of the velocities. And really, this is a function of time. Okay, so if we write it this way, then now we have completely finished our reduction to a first order ODE, right? Because we can write that d big X dt is some function of big X and t, which can be written in the form that we had on the previous slide. Now, if we have a collection of particles, like a bunch of stuff tied together by springs, then now we have a bunch of different x's and v's, and we can combine them into a long vector with lots of little pieces, kind of like we've shown here. And so at the end of the day, that same reduction still applies, right? So the derivative of x1 is v1, the derivative of x2 is v2, and so on. And then the derivative of v1 is big F1, which collects all of the forces on particle 1, and so on. Now, this is the kind of calculation I encourage you guys to also just try on paper at home and make sure that you understand. So as another example, let's say that I want to solve the second order differential equation y double prime equals 2y. Essentially, all I've done is said that I can write that as a different first order equation, y prime equals some other thing like v prime is 2y. That's it. So I'm just adding a dummy variable to keep track of all the derivatives. By the way, here's something that I want you guys to try at home, which is to see if you can figure out how to reduce an even higher order ODE to a linear one. So for fun, why don't you guys on Piazza discuss taking the problem, the third order problem, y triple prime equals cosine of y, and see if you can write that as a first order system of ordinary differential equations. Okay. So let's introduce some additional vocabulary words. One that's kind of useful is something called phase space. And this is essentially the space of values x. So remember that our ordinary differential equation takes the form that I've boxed here on the slide. And now let's think about that a little bit. So let's say that x is two-dimensional. If it's higher than two-dimensional, it's kind of hard to draw on our PowerPoint screen. So maybe here's like x1 and here's x2. So what is this equation saying? Well, it's saying that I can give you the rate of change of x at a given point. So if I'm like sitting here and I evaluate my ODE, it gives me a vector, which is how x is changing. Okay, so if I look at all the possible locations x, then what I get is a vector field, right? And that's telling me if my current configuration x is here, this is how it wants to change. And this is called phase space. So the example shown here is for a pendulum. So let's make sure that we can understand that. So in a pendulum, there's again an F equals ma kind of thing going on, but we're going to reduce it to first order. And when we do that, instead of having one variable, like the angle of the pendulum as it swings back and forth, we have two. So here I've chosen to give you the position of the pendulum and the momentum. This is parallel to velocity, so it's perfectly fine. And now we can begin to read this, this particular diagram. So let's think about pendulums for a second. Remember, a pendulum is, it may be a piece of string with a weight held on the end, so it swings back and forth. So the origin here, if I'm sitting at the origin, that means that my pendulum is at position 0, so like right at the bottom, and it has no velocity, so it just stays there. And that's what you see because your vector field is 0. Now, as I move farther out, even if my initial momentum is not 0, my initial position is the pendulum kind of pulled out that way. So when I let go of it, the pendulum's going to swing back and forth. And indeed, that's what we see, right? So the angle increases and then decreases, increases, decreases. Okay, so that's what's going on in our pendulum. At this extreme point here, this is the pendulum sitting right upside down. It actually can be stationary right at the intersection of these lines. If I move far enough out and we take a look at the paths, they no longer go in loops again. And let's think about what that means for our pendulum. Well, if I move far enough out, that's like the initial momentum of my pendulum is really high. That corresponds to the case where I have a pendulum, I give it a kick at the beginning and it swings in circles and circles and circles. And so the angle just keeps increasing. Okay, so that's how to read these phase space diagrams. So now our task is clear in the graphics world. What we're trying to do is to integrate our ordinary differential equation or solve it numerically. Another term for this, sometimes people use is quadrature. I think of quadrature more like the process of approximating an integral. So today we're going to talk about one simple option for how to solve this problem. And then in our next lecture, we'll talk about some more advanced techniques. Okay. So our simple option for solving the ODE looks something like this. So remember that our ordinary differential equation is just dx dt is f of x comma t. I'm going to do something notationally, which isn't particularly kosher, which is to multiply both sides by dt. And what do I get? I get that the change in x is like a change in a little t multiplied by f. And that actually suggests a very simple algorithm. This is known as Euler's method for solving an ODE. And it looks something like this, which is I choose a step size h. This is kind of like our dt from before. And given an initial condition x naught, I can take a step from t naught to t1, which is t naught plus h, by doing the following. I start with my initial condition, I take my field, I scale it by h, and I add that to get x1. Okay? Notice that that's just taking this formula here and adapting it to a positive value h. So in other words, all I'm doing really is replacing dt with a small but finite number. Okay. Here's what it looks like visually. So here on the screen, I show you a vector field. And let's say that my current position is x of t, like what I show you on the screen. I evaluate my vector field. That gives me f of x comma t, which is telling me how x wants to change. I scale that by h. Typically, h is a small number, so it gets shorter. And I add that to get x of t plus h. Now, did I actually solve my ODE when I did that? No, this is an approximation, right? Like in this field, probably the flows are like curves or something. So it's tangent to that curve, but the two diverge just a tiny bit. But notice that the smaller h is, the more accurate this integrator is. Yeah, and so that basic observation, a different way to put it, is that the step size controls the accuracy of your integrator. If you take smaller steps, you'll more closely follow your curve, but it's going to require more computation to get to the same frame in your animation. In fact, you may have to take several small steps of h per frame in your 30th of a second before you have to display the next frame on your screen in order to get an accurate physical simulation. So here you see what that looks like, right? So remember that Euler's method is in some sense piecewise linear. It's a fancy phrase for saying that I follow the velocity field along a line for some positive amount of time. And notice that as the step size gets smaller, I get closer and closer to the actual solution of my equation. So let's see another example of Euler's method. This is a really famous ordinary differential equation, which says that f is minus y comma x. So let's think about what that looks like visually. So here's the x-axis, here's the y-axis. So let's say that I'm at x equals 1, y equals 0. Notice that, well, in that case, the velocity is going to be 0, comma 1, so it looks like that. Similarly, at y equals 1, x equals 0, I'll get minus 1, and so on. And indeed, if you plot your vector field in all kinds of different places, what you'll see is that its flow lines basically trace out circles. Okay? But what's going to happen if I use this Euler method? Well, let's say that I'm tracing out a circle, and maybe I'll try a different color here just for fun. Okay, so here's my initial condition, and I follow for a positive amount of time. Well, now I'm actually, so circles have the property that they're constant distance from the origin. Oh, man. But because I moved this along a straight line, that's no longer the case. I actually got farther out from the origin than where I started. And indeed, one thing that you'll see if you solve using this thing is that you get farther and farther away. Here's a better visualization. I'll try to hide my PowerPoint struggle. You can see that Euler's method with a big time step actually spirals out of control. That's because Euler's method can be quite inaccurate. And in fact, Euler's method, the term that we often use is that it's unstable. What that means is that it actually adds energy to your system and leaves the solution curve. So rather than getting circles, you get spirals, and the speed at which that spiral zooms away from the origin has to do with how big h is. That makes sense in the sense that if h is really big, you're somehow moving away from those differential relationships that your ODE solver is trying to capture. One thing that's worth noting about this particular setup, it's very easy to kind of convince yourself like, okay, yeah, it diverges, but that's just a sign that I used too big of an h. You know, your system exploded. That's bad news. Of course, in a video game, that could be a total disaster, right? Your whole video game could explode. One thing that's worth noting is that this actually spirals outward no matter how small h is. It's just a matter of time. Why does that matter? Well, let's say that I'm including a physical simulation component in a video game. I don't know how long people are going to play the video game. And so if I leave this game on its own devices and just sit there and wait, if I'm using Euler's method, it'll slowly add energy, and it might be that the game slowly explodes. So you have to add some hacks to kind of tamp down the motion and counteract that. In fact, here's a screenshot from one of my own research papers where this became a problem. In this thing, we were trying to come up with a method for elastic deformation. So like I have a shape and I want to be able to mark a point on it and pull it and have the shape deform in response to that. And we had a piece of code that was doing this by integrating an ODE. And we had a really funny bug. You can actually see it in our research paper if you Google for that thing. Where if we took the head of our little monster here and we shook it up and down a few times and then put it back, the head actually doubled in size, right? You can see the original image down here. And actually the reason for this strange phenomenon was exactly what we've talked about in class today, that Euler's method was being inaccurate and actually increasing the size. So what are we to do? Well, in practice, there are many other accurate alternatives to the Euler method for integrating ODEs. And in the next lecture, we will introduce quite a few of them, including midpoint, trapezoid, and RK integrators, as well as implicit techniques that are even more stable. And in fact, there's all kinds of cool integrators out there for physical systems that try to preserve different properties and have them basically not explode if you wait too long. So here's kind of a fun animation comparing a few different options from my friend Andy here. So Euler's method is sometimes known as an explicit integrator. We'll talk a little bit more in the next lecture about what that means. Essentially, an explicit integrator means that if you let it go on its own devices, slowly the energy of your physical system will increase as a function of time, and that's thanks to inaccuracies in your physical solver. A different class of popular physical solvers in graphics are implicit. Again, we'll talk about that more later, but the end result is that implicit solvers actually dampen the physics and decrease the energy. This can be a good thing in video games because at least they don't explode, but they can create for some pretty boring motion. And then very recently, a kind of a modern topic of research is to define things called variational integrators, which have really cool properties. For example, that they actually preserve energy, or like that the energy averages out to some constant over time. So if you watch this little animation again with this guy flying on a pendulum, the explicit integrator explodes, right? Because it's adding energy to the system. The implicit one, the pendulum just kind of comes to a stop. And the variational integrator, it just keeps going for all time. So let's watch that again. I feel bad for the guy on the left. Okay, but now that we at least have one technique for simulating a physical system, let's talk a bit about what we could do with it. Namely, how can we do some modeling and actually create interesting motion on the computer that is modeled as an ODE and then solved using the types of techniques like forward Euler method that we just covered. Of course, in order to do that, if we write down f equals ma, well, we need to define our functions f. So a force, right, this f and f equals ma is basically a way to change the motion in a system, right? We all know this from physics class, right? Newton's, I always get the order of Newton's laws wrong. I believe it's Newton's second law, tells us that, an object in motion remains in motion, and essentially the idea is if you don't act on an object with a force, it'll just fly along with constant velocity. So we need to come up with interesting forces to create interesting motion in our animated content. And of course, these forces can depend on the location of the particle, what time it is, the velocity of the particle. Any of these things is perfectly fine. The force cannot depend on the acceleration of your particle. That would be non-physical. I suppose it maybe can, but then it wouldn't really fit into Newton's laws. But it would be okay in an animated world. I'd be curious to see what that looks like. So for point masses, we can think of forces like little vectors that are acting on your point. And thanks to Newton's third law, right, F equals ma, we just sum up all of the forces to get the total force on our particle. So for the next couple slides, let's talk about the types of forces that we want to model in a particle system. So probably the simplest force we might model is gravity. Gravity is a constant force, right? It's just equal to m times g, where m is mass, g is acceleration due to gravity. I think we've all seen what that looks like. Here's a ball falling by gravity, in case you're curious. One hack is, let's say that I want to simulate smoke. So smoke particles, the next time you light something on fire in a controlled fashion, of course. Take a look at the smoke, and one thing that you might see, at least in small scales, is that smoke moves faster as it gets farther away from the source, at least visibly. And so one way to handle smoke using a particle system might be to take gravity and just change the sign. So the smoke starts flying upward and it increases in velocity as you move up. You do a similar thing for buoyancy too, like in fluids. Of course, if you're writing a video game that's a slightly larger scale spatially, then maybe rather than simulating gravity as a constant, you actually have to simulate it using the law of gravitation here, right? That the force of gravity is equal and opposite, and that it has magnitude equal to gmm over r squared. Remember, so r is like distance. So the closer things are, the bigger the force of gravity. Now, there's a couple concerns here that are worth noting. Now, this is our first example where objects are not moving in a fashion that's independent, right? In order to compute the force acting on one of the planets in my system, I need to know the positions of all the other planets. That's perfectly fine. We can do that by adding up all of these different forces. But let's think from a computer science perspective, what could go wrong? So let's say that I want to figure out all of the forces on some particle I. Well, what do I have to do? Well, I have to sum over all of the j's, the F exerted on I from j. Be honest, I don't remember the sign. This is, plus or minus. Okay, so if I want all of the forces on all of the particles in my physical system, well, in essence, I end up with a double sum. So this is actually order n squared time. If I have n planets in my system, computing the forces on every pair is quadratic in the number of particles. Now, even if you're not doing gravity, I think we all like to model particles moving around by influencing one another. If every particle affects the force on every other particle, the basic takeaway here is that computationally, the amount of time that you'll need to do your math scales quadratically in the number of particles, which can be quite expensive. One of the really amazing things is that some of the modern graphics cards can actually handle this. So here's a demo from NVIDIA from a few years back, which is just doing brute force like quadratic number of computation and simulating a huge number of particles flying around according to gravitational force. Now, this is a brute force algorithm. It's just evaluating that double sum. Specifically on gravity, just a quick aside, there are actually techniques out there that can do better. I encourage you guys to read about this because it's kind of cool. Essentially what they do is they say that if they're is a big clump of planets and it's far away from me, I can roughly take that clump of planets and approximate it with one planet whose mass is equal to the sum of the masses in that clump. And the dynamics will be about the same. And so there are techniques out there. The most famous one is called the fast multipole method, which essentially do that kind of clustering and can get order n, or probably more like n log n time, which is one of the ways that you can accelerate that physical system. Okay, but gravity isn't the only force that we want to simulate. There are many others. Another one which can actually help us counteract some of the instability of forward Euler method is viscous damping. So in viscous damping, this is a force that is proportional to velocity rather than changes in position, or rather than differences in position. So the idea of viscous damping here is, let's say that I were a really fast runner. I wish I were. Eventually, if you run fast enough, you actually feel a force acting opposite your direction of motion, which is the wind resisting your motion, right? We all know this from like talking about terminal velocity, right? If I drop something from the air, the wind resistance means that it won't just accelerate arbitrarily. Eventually the wind will be kind of counteracting the force due to gravity. And so this can help settle your system. And actually a small amount of viscous damping can stabilize your solver beyond what you would get with some of the crazy things we saw before. On the other hand, too much damping makes your physics look like glue. Okay. Another thing that people do to model the forces in a particle system is actually to just come up with cool force fields that sit outside of the set of particles. These might be artist designed, or they might be physical in nature, right? So for instance, the wind is a nice example, like I know that the wind is circulating like that. So as I, walk, I have some character walking through a scene, the force that they're experiencing due to the wind changes depending on their position as they walk through. Of course, these can add energy to your system once again, so you might have to dampen your motion even more. In our next lecture, when we talk about better integrators for physics, we won't have to have quite as much damping. So here's a fun example of an artistic model for this sort of thing. So in this research paper in 2007, essentially what they proposed was to just procedurally generate interesting force fields that act on particles to create flows that look like, fluids and so on. So actually all the particles, I believe, in the system are acting independently of one another. The only thing that's happening is it's reading the force on the particle from some field sitting underneath, and then the particle moves around according to F equals ma. There's not like springs or something coupling them together. Let's take a look at what that looks like. So you can see that you get some really complex and interesting looking motions just by creating vortices in this force field, even though the particles aren't actually interacting with one another. There's no pairwise force. This is pretty cool stuff. Let's look at another one. Okay, and so from a computational perspective, this kind of a technique is really valuable, right? Because essentially what it's allowing us to do is to get fluid-like motion without doing all this crazy computational work to simulate a fluid by solving the equations of motion, which are quite complicated. There are other kind of more exotic forces out there. Some of them are physical, some of them are just things that people have modeled. So another nice example is something called the Leonard-Jones potential, or sometimes I think it's usually the 612 potential, because those are typical choices for M and N. So the idea in Leonard-Jones potential is to make a force field whose profile looks something like what you see in the plot on the slide here. So the idea is that if two particles get too close to each other, right, that would be like the left-hand side. Well, in that case, the particles got too close and they violently want to repel. Then there's some sweet spot where they attract each other, but the attraction becomes weaker as I move farther and farther out. So things like very weakly attract each other, and there's like some happy neighborhood where they want to be. If they get too close, then they repel. Again, unfortunately, to use this sort of a force, at least without a method like fast multipole, you need to do an n squared style computation, right? Because these particles are not independent of one another. Leonard-Jones potentials are useful for all kinds of interesting simulations. You can see here the type of thing that happens in this simulation, which is that these balls kind of want to be close. They kind of want to stick together into a unit, but not so close that the whole thing just collapses down. Here's a second example. So you can see here that there's essentially like the red material and the blue material kind of want to keep together a little bit. Or I think probably the more compelling example here is if I wanted to simulate cracking or tearing. Here's one way that I could do it, which is to model my object by using this kind of potential. And then if I slice in between, I cut the potential, you can see that the pieces want to hold together and hold their shape until they're torn apart, and then they don't care quite as much. So other sources of force that appear and are really important to handle in a graphic system include collision. So obviously, if I drop a ball on the ground, the ball gets an impulse and bounces back up. We'll talk about some of the basics of collision later in this course. They're a little bit tricky to resolve mathematically, right? Because you have to come up with the right force so that the objects don't interpenetrate. Maybe more subtly, not only do you have to come up with that force or impulse, you also have to actually detect that two things collided to begin with. And that's actually not such an easy task. So for example, if I have two triangle meshes and I want to know if they interpenetrate, that's actually quite difficult computationally. First of all, to write down any algorithm that can detect that, and an efficient algorithm that can detect whether two triangle meshes are colliding is quite difficult to implement. So there's all kinds of fun eye candy that you can watch online. NVIDIA, the graphics card company, releases a lot. I thought for fun we can play another one where they're ejecting around 500,000 different smoke particles sitting behind a car. These are largely just to show off that your graphics card is really good at this kind of computation and can actually scale to a pretty large number of particles. So let's see what that looks like. Forgot how many things they have to tell us. There you go. There's a pretty crazy car flying around and all the fluid motion that's happening behind it. Okay. So far, basically the forces that we've tried to define are largely designed to try and capture physical systems, but they can be used to model other motion. For example, flocking birds, fish moving around, following each other, crowds of humans is a big one. Just by, rather than trying to figure out the physics of a system, just modeling the dynamics that we think we observe. So a good example of that, which is a really popular course project in 6837, incidentally, is to simulate something called a boid. So a boid is a little bird in a flock of birds. And essentially in the boid simulation universe, I'm trying to get interesting motion of particles flying around to simulate a pattern of birds flying together. Incidentally, let's look at the word boid for a minute. Anybody have any guess? So boid is short for bird-oid. So it's like a bird-like robot, I suppose. And essentially the idea here is that as the birds fly together, you're going to model forces on these birds that want them to kind of flock in a particular pattern. So in this birdoid setup, typically there are a few things. So like you don't want the birds to get too close to one another. So you might model a force that looks at nearby birds and then adds a force repelling you from them so that they don't clump together too much. The birdoids, actually, they maintain their position and velocity. So one thing you could do is look in a neighborhood of your boid, and if you notice that everybody's pointing in a particular way, then you correct your own velocity to point in a similar direction. And then finally, kind of similar to that Leonard-Jones potential, maybe if you're too far away from the flock, then you actually add a force pulling you closer to the flock, so that all the birds fly together. What's that Mighty Ducks line? Ducks fly together here. And the end result is actually really impressive. So let's watch a little video showing you what kind of you can do with just some simple forces governing the motion of these birdoids. Boids. I would talk, but I think the video that I record gets a lot worse. You can see this is a very early algorithm. It's been around a long time. You can add predators and prey and obstacles quite easily to this system. Here's another example. I believe the audio in this particular video clip is kind of strange. So here you can see they made two different types of boids that kind of add repelling forces to the system. And then I think they're just rendering it with little flapping wing animation. I don't think that there's anything intelligent going on there. And you can see that the motion here is really impressive. I've included a link in the slides to a demo that you can play with boids in your browser, and I highly recommend you click it. It's a lot of fun to interact with. Particle systems are used all over the place, and when we start talking about boids, that's just the tip of the iceberg in terms of software that people define, where rather than thinking of the forces on your particles as physical things, they're just artistically modeled. So a different one, there's this piece of software called Massive out there. I think it was used for Lord of the Rings, where you might want to actually simulate human characters moving around. And that way you can get these, battle scenes with tons and tons of people fighting. So you can see here the end result of huge amounts of characters that are digital pouring into one another, which thankfully is not a ton of actors with spears. I would not want to have that acting gig. Some actors with spears, but not a ton. So let's tie up a few loose ends here. Of course, one thing that we mentioned at the beginning of lecture is that particles are generated by emitters. Often an emitter is just like another object in your code. A very typical thing to do is to try to control the number of particles emitted per second. So one way that you could do that is to record the last time you emitted a particle, and then essentially increase the probability of emitting a particle as time goes on, or so that you try to average out to the right number of particles over time. So there's all kinds of software out there where actually artists can design particle systems. This is pretty cool. So there's some software out there called Particle Effects, which is one kind of early one for video game systems. And essentially what you can do is maybe give rules like, when my particle is in this region of space, I'm going to render it this way. Maybe here are some equations for different forces on my particles. Here's where they want to move in the force field, all that good stuff. How do you think that they define these? Well, once again, it's using splines. So here you can see, for example, I think down on the bottom right, the artist is controlling the color of the flame particle as a function of the position. And so the kind of funny thing is, particles are simulated using Newton's laws, but of course here the artist is just inventing physical laws to create the motion they want. This is a great example of physically plausible but non-physical motion. And so I've included a link in the slides to an online tutorial where you can see in action the artist slowly designing their particle system for the Unreal Engine. So there's this kind of fun user interface where you see the particle system, you can change, parameters of how it's rendered, maybe something about the motion, the color and so on. And by the time you get to the end, you get a nice little puff of fire and smoke. Now, finally, one thing that's worth noting is that you don't have to render particles as particles, right? So far we've just shown little dots. But for example, maybe I shoot my gun at some piece of metal, a bunch of sparks come off, then maybe rather than rendering it as a point, I render it as like a line, or a cylinder that's aligned to the motion of the particle. I think is a pretty typical one. Or a different thing you might do is, for example, here we have a video game, with shooting and fire and so on. Obviously, the look here is quite complex. The number of particles is actually not so large. And the way that this is created is by using objects called sprites or billboards. And so sprites or billboards, let's see what this looks like, are like little tiny images like what you see on the upper left here, where what you do is when you render the particle, rather than just rendering a point, you take this image and you just splat it down in the position of the particle. Now, why do we call them billboards? Well, typically what you do is this rendering happens in image space, meaning that the way that it's drawn is always facing the camera. So like if I, moved and tried to view this explosion from some other side, these things would still be facing the camera. It's kind of a common hack in the particle-based simulation world. Okay, so as a quick recap, in our previous lecture, we talked about keyframing, procedural rendering. Today, we just got started with particle systems, talked about forward Euler integration, which is really simple, right? If we have a formula for dx dt, essentially we just multiply both sides by dt. And then we talked about some different forces that we might use to model a physical system. In our next lecture, we'll talk about mass spring models in more detail, and that's going to allow us to model stuff like cloth and hair to get those particularly critical physical effects in our graphics system. So we'll talk to you later.